When we were last talking about equilibrium, we saw that we could describe the position of an equilibrium quantitatively if we knew something about the state of the system, perhaps its color. We could say that the equilibrium had shifted to make the solution more pink or more blue in a cobalt example. However, we really want to get quantitative. That's one of the big themes of this semester. So how do we do that in the context of equilibrium? We saw that we were able to be quantitative with Gibbs free energy, entropy, and enthalpy because those were quantities we could really get in the lab and measure. Well, when it comes to measuring the properties of a chemical compound in solution or as a gas, you've seen many times in lab that you can measure a concentration or a pressure. So how can we use that to get quantitative about equilibrium? Well, let's imagine for a moment a chemical reaction. This is a completely arbitrary one, involving two reactants and two products. Those might be reactants A and B in equilibrium with products C and D. The nature of each chemical compound, or the chemical formula, is denoted by a capital letter, while its stoichiometric coefficient is denoted with the lowercase letter. The tool that we're going to use to be quantitative about equilibrium is called the equilibrium constant expression. So the equilibrium constant is typically described with a capital K, and we put a little EQ subscript underneath it to show that it's a equilibrium constant. And that equilibrium constant is related to this reaction in the following way. The concentration of each of the products raised to the power of its stoichiometric coefficient divided by the concentration of each of the reactants, likewise raised to their coefficients. That exponential part may seem a little bit weird at first, but it starts to make more sense when you think about the fact that if you, for instance, were forming two C's, you could either write 2C or you could write C plus D. And as a result, you would want to put in C times C. So what's the value of this? What is this telling us? Well, it says that some constant is going to describe the relationship between the various concentrations. So if our equilibrium constant is really big, that represents a reaction that favors the products. And by comparison, if our equilibrium constant is really small, it must mean A and B are quite large, and that's a reaction that's going to favor the reactants. Now, this is really, really handy because it tells us about how to adjust our system to account for changes in concentration. That's what we're going to be looking at in our next segment. But before we do that, there are a couple of aspects of how these things are put together that wind up being important to making them work correctly. The first is that this expression is ultimately going to make a unitless number. And at first, that might kind of bother you because we have a whole bunch of concentrations here. How can we possibly make a unitless number from things with units of concentration, something like perhaps molarity? Now, if you recall, molarity means moles, amount of stuff, per liter, amount of area or space. That effectively means that anything that has a pressure is also more or less describing a concentration due to the ideal gas law. So you could kind of imagine how this might work for pressure or for concentration, but in either case, unless you get very lucky with your reaction, you're not necessarily guaranteed, it would seem, a unitless number over here. Well, one of the aspects of how this works is that these brackets are denoting that each compound in the equilibrium constant expression is being divided by whatever its conditions would be at standard state. That's good because our conditions at standard state are things like 1 molar. So if we divide by 1 molar, all we're doing is stripping out the units. So I know I've spent all semester telling you how important it is to keep units with your numbers. Well, this is a time that we're not quite going to be doing that. There's something else too. If you divide a compound in solution by its standard state, well, that's 1 molar, and it switches its number over to molarity. You can also imagine how the same would be true if you divided a pressure. Dividing anything by 1 bar is going to give you a unitless pressure number. But recall that for a pure substance, something like a block of aluminum or a jar of water, that substance is in its standard state, but that standard state is not necessarily going to involve a concentration. In essence, you can't change the concentration of pure water because if you added anything else in, it wouldn't be pure water anymore. As a result, anything that is not a gas or in solution can't be included here because dividing it by its standard state would turn it into 1. So that means that we're talking about dividing by conditions at their standard state and not including pure substances as either solids or liquids. But we will include things that are gaseous or in solution. So we now have an approach that we can use to start to put a number to a particular system. Now, let's look at a quick example. I want to go back to that equation that we were just looking at in the last segment, the cobalt compound. So in that case, we had I want you to take a moment and think about what the equilibrium constant expression for this chemical reaction would look like. Okay, let's write out that expression. On top, we want each of our products. Should the water be on top? It shouldn't. And in particular, it shouldn't be on top because that water is in liquid phase. On the bottom, we want each of our reactants. And note that we're raising that chloride to the 4th power because there are 4 moles of chloride consumed for each mole of cobalt. Up next, we're going to be looking at how to use this equation to get some meaningful information about a reaction. In particular, we're going to be starting by looking at weak acids and bases.